Good morning and welcome to Tech 240 on Wednesday, March 31st. The purpose of today's video is to do a few review problems and talk about Exam 2 because Exam 2 is scheduled for Monday, April 5th. That's the next class day. The exam is going to consist of about 50 to 60 questions. I don't know exactly how many right now, but it'll be in that ballpark, maybe give or take 10 or so, something like that. And the format will be very similar to Exam 1. It'll be structured very similarly to what you took in Exam 1 about a month or so ago. There will definitely be some multiple choice questions. There will definitely be some true-false questions. And there will definitely be some calculation questions. The best way to review for the calculation questions is definitely by reviewing all the labs and making sure that you understand how to do all of the problems and all of the labs that we've done in this section of the class. The best way to review for the more conceptual-based questions, like the multiple choice and the true-false questions, is probably by reviewing your lab manual, by reviewing your notes that maybe you took during the synchronous sessions, or by reviewing the videos for the asynchronous sessions, and reviewing those concepts that we've talked about along the way. The exam is going to open at midnight on Monday, April 5th, and then it will close at 11:55 p.m., almost 24 hours later. And you can pick any 3-hour window in that day to take it. So the time limit of the exam is 3 hours, just like it was for Exam 1. I don't think the 3-hour time limit will be a major factor because I will write this exam very similarly to the way that I would write the exam if we were taking it in person. So I think this exam should be able to be completed in an hour and 50 minutes, but I'm giving you 3 hours to do it. So I don't think that it should be, time should be a major factor. I don't think so. Make sure when you sit down to do it for that 3-hour window, make sure, first of all, you give yourself the full 3 hours. So don't sit down and start taking it at 10 p.m. because then you only got less than 2 hours until it closes. So make sure you start at least by 9 p.m. to make sure that you got the full almost 3 hours to do it. And also make sure that you have a writing utensil and some scratch paper for the calculation problems. Probably want to have your lab manual out for reference. A calculator, if I didn't say that already, definitely want to have that available. Your labs, you might want to have those to serve as a resource. You can also use the videos as a resource. They might not be the best resource because it might take you a while to find what you're looking for if it's in the videos. So if you do go back to a lot of the videos, then you might run into that 3-hour time limit for the exam. But if there's just a couple of things that you need to go back and take a look at in the videos, they're there. They're available for you. The only thing, once again, that you can't use is each other. So I don't want you to be texting back and forth or conversing about the answers to different questions. All right, so what else? I think that's about it. Let me know if you have any other questions. I do have office hours on Thursday again, so if you have any questions that come up, you can feel free to stop by my office hours, and I'm happy to talk about anything in office hours. So let's go ahead and do a couple of review problems, and then we will talk about the concepts and the different materials that are going to show up on Exam 2. So I'm going to switch over to the document camera. All right, I've got 3 example problems that I'd like to do, and I'll show them to you in order. And then, as usual, what I'd really recommend that you do is pause the video, solve the problems, and then come back and we'll talk through them together. So here is the first problem. It says, what is the polarity of the applied voltage in this DC motor? So there is going to be a DC voltage applied right there. But the question is the positive side on the left, negative on the right, or vice versa? Is the positive on the right, negative on the left? So what's the applied voltage right here? You can go ahead and draw in the battery or voltage source right here. to answer the question. We know that we have the direction of the magnetic field from right to left because we have north on the right, south on the left, and we're given the rotation direction of this motor. We're told that this armature is rotating in a clockwise direction. So given that information, given the direction of the magnetic field and the rotation direction of the armature, you should be able to figure out what is the applied voltage here in this DC motor. Okay, so that is the first one. The second one looks like this. We're told that the output frequency from this generator, this AC generator, is 80 hertz, which is kind of an unusual output frequency, but you know, whatever. And we want to know how fast should this rotor spin. So the armature is on the rotor, and we want the output from this armature to produce some voltage. We don't care about the voltage in this problem, but we definitely want the frequency of the output to be 80 hertz. So how fast should we make this spin around inside the stator? So how fast should the rotor spin to produce 80 hertz? That's number 2. And question number 3 for today. We have a coil on the armature of an AC generator, and that coil has 1,000 turns of wire wrapped in the shape of a circle. And we're told that the magnetic field changes from 0.5 Tesla to 1.5 Tesla, and that happens in 0.2 seconds. We're told that the output voltage from this armature right now at this point in time is negative 300 volts, and we want to know what is the radius of the armature. Okay, so that is the third question. So what I'd recommend that you do right now is pause the video and then solve all the problems, and then unpause the video after you've solved them so that you can listen to the answers. Okay, so I will assume that you have paused the video, solved all the questions, and now we're ready to go through the answers. So number 1, what's the polarity of the applied voltage in this DC motor? So because it's a motor, we can apply our left-hand rule for motors. That gives us the relationship between the direction of the Lorentz force, which will result in motion, and the magnetic field, and the direction that current is flowing through the armature. So we take our left hand, we just got to make it fit into this particular situation. So I'm going to apply, it doesn't really matter. I'm going to apply the left-hand rule for motors to the left side of the armature first. So I know that my first finger needs to point from left to right. I'm going to have to get up and move around a little bit to make this work. So my first finger needs to be going from right to left. And I know that at this point in time, because the armature is rotating clockwise, at this point in time, the left side, I can go ahead and draw this in, the left side of the armature is moving up toward the top of the page right now, and the right side of the armature is moving down towards the bottom of the page. I know that because I'm told the armature is rotating clockwise. So at this point in time, that's moving up toward the top of the page, that's moving down toward the bottom of the page. So if I apply the left-hand rule for motors to the left side of the armature, my thumb needs to point up, and my first finger needs to point from right to left. And so what happens as a result of that is that my second through fourth fingers, you can't really see them because they're pointing away from you. They're pointing away from the camera towards the page, into the page. So if I draw that on my drawing, it looks like this. The current is going into the page like that. So because of that, I suspect that current is going to be coming out of the page on this side, but let's double check it to make sure that we are correct. So over here, my first finger still needs to point from right to left. And now my thumb needs to point down towards the bottom of the page. So it needs to be like this, where my thumb is pointing down towards the bottom of the page. and my first finger is pointing from right to left, and so therefore my second through fourth fingers are indeed pointing out of the page toward you or toward the camera. So I can draw that. So there's my current flow, and that helps me answer this question because I know that the current is only going to flow if we have a complete loop, if we have a circuit. So I know that the current is going through this side of the armature out of the page, and then it's going to be going down like this through the split ring commutator, and then down like this, and then it's going to be going from right to left. So the current must be going like that, and then completing the circuit. So it's going to be going like this and like this. So there's our complete circuit. So we know that current goes from positive to negative. So the answer is that we must have the positive side over here and the negative side over here, so that current will go from the positive side through the loop, through the circuit, and then back to the negative side. So I could draw that in. It looks like this. So there is our answer, with the positive side on the left and the negative side on the right of the DC applied voltage. So that's number one. Moving on to number two, we're told that we have this generator. It's an AC generator, and the armature is on the rotor, and we want to produce 80 hertz of AC electricity. That's the frequency. How fast should the rotor spin? And we actually have an equation, a fairly simple equation to do this. And the equation is N, which is the rotor RPM, equals 120F, where F is the output frequency, divided by P, where P is the number of poles on the magnetic field. So how many poles do we have? We got to count them. 1, 2, 3, 4, 5, 6. So we have 6 magnetic field poles. So P is going to be 6, and our F is going to be 80 hertz. And all we have to do is plug in numbers and find N. So this is really pretty simple. N equals 120F divided by P. Plug in your desired frequency, plug in your number of magnetic field poles, and then plug it into your calculator. And you'll get that N, the rotation speed, equals 1,600 RPM. That's all there is to that one. That's number two. And the last one, number three, is a little bit more involved, but still not too bad. Here we have an AC generator. We know the number of turns of wire on the armature, and we know the magnetic field and how it changes and the amount of time it takes to change. And we know the output voltage, and we're just trying to find the radius of the armature. So because we're trying to find a relationship between the number of turns, the change in magnetic field, the change in time, the output voltage, that pretty clearly sounds like a Faraday's law problem. So I would start by writing down what we know. We know the number of turns. We know the change in time. We know the initial magnetic field, the final magnetic field, the induced voltage, and the only thing that we don't know that is relevant to Faraday's law is the area of the armature. So we don't know that, but if we can find it, because it's the only unknown, so maybe if we can find that, we can use that combined with the knowledge that the armature is in the shape of a circle, and we can find what the radius is of that circular armature. So that's what we'll try to do. So we can write down Faraday's law. Here's a basic Faraday's law equation. And we know that the change in magnetic flux is equal to the area of the armature times B2, that's the final magnetic field strength, minus B1, that's the initial magnetic field strength. So all I did from here to here is I expanded delta phi, change in magnetic flux, into this. Area times the quantity, B2 minus B1. And now I know that, I know that, I know that, I know that, and I know what the induced voltage is. The only thing here I don't know is the area. So I can rearrange this equation and solve for the area. So that's what I'm going to do.
To solve for the area, I'm going to multiply both sides times delta t, and then I'm going to divide both sides by n, and I'm going to divide both sides by the quantity b2 minus b1. All right. Also, I'm going to multiply both sides times -1 because I want to get the area, not the negative area. So when I do all of that, I get the area equals negative, that's from the negative sign there, negative E induced times delta T divided by N times the quantity B2 minus B1. Now I can just plug in values. Be careful of your negative sign here. We have negative E induced, but E induced itself is negative 300 volts. So be careful. Make sure you plug in your negatives where you need them. So we actually have negative 300 volts times 0.2 seconds divided by 1,000 turns. That's N times the quantity 1.5 Tesla minus 0.5 Tesla. That's B2 minus B1. Now you can plug all of that into your calculator. The negative times the negative is going to cancel out, and we're going to get a positive number. And the area that we get is 0.06. And remember, when we're dealing with Faraday's law, the area that we plug into this equation always is going to be meters squared. So our area is 0.06 meters squared. Now, that's not quite the answer, so we're not done yet. That might be the hard part, or at least the part that requires the most algebra, but it's not the end because it asks for the radius of the armature. So here's what we got so far. We know that we have this circle, this circular armature, and we know the area of that circle is 0.06 meters squared. We also know that the area of a circle is pi r squared. So if we know the area is 0.06 meters squared, and we also know the area is equal to pi r squared, we can set this equal to this and solve for r. So that's what we're going to do. We're going to say 0.06 meters squared equals pi r squared. We're going to want to solve for r. So how do we do that? We need to divide both sides by pi. Then we're going to get r squared equals 0.06 meters squared divided by pi, which is 0.0191 meters squared. Now we know r squared, but we want to get r, so take the square root of both sides. And when you do that, then you will get the radius is equal to 0.138 meters. And that's fine. You can leave it like that. You could also convert it into centimeters by multiplying times 100, so it'd be 13.8 centimeters. But just be careful in these types of problems, because maybe I would ask you for the radius, maybe I'd ask you for the diameter, maybe I'd ask you for the area. Also, maybe I'd ask you for the answer in meters, maybe I'd ask it for it in centimeters. So just pay attention and be careful to answer the question as it is asked. All right, so that is the answer to number 3. Now let's go ahead and let's do a review of the concepts that we have talked about in this second third of the class.
Okay, I'm going to write out some of the topics that we have talked about in this second third of the class. First of all, I've said this before, but the exam 2 is not meant to be cumulative. So you won't see things like KVL and KCL on there. However, there are a few things that you just can't get away from in a course on electricity like this one. So things like Ohm's law and the power equation, P equals IV, and the energy equation, E equals P delta T, things like that you can't really get away from. So I expect you to be able to use those equations if they were to come up on a question in this exam. When we got into this section of the class, the first thing that we talked about was magnetism. And we talked about how it is created, or what causes it. And we talked about drawing magnetic fields. I'll just abbreviate them B, drawing magnetic fields, and connecting the poles and drawing them from north to south. How to draw stronger magnetic fields, what indicates a stronger magnetic field. So I'll write some of those. drawing the lines of magnetic flux from north to south, connecting the poles like we did in that very first lab, and drawing how to show on your drawing that a stronger magnetic field exists. So drawing a stronger magnetic field. The way we drew that was by drawing more and denser lines of magnetic flux. All right. Also, the idea that there is no such thing as a monopole. We only have dipoles. If you have a bar magnet, you're always going to have one side be the North Pole and one side be the South Pole. Okay, then we talked about electromagnetism. And we talked about electromagnets. That was actually the first thing. Electromagnets. And we talked about how to change the strength of the electromagnet. How to change the strength of the electromagnet. Don't get that confused with, later on, we talked about how to change the induced voltage in a generator. All right, so there were 3 different ways that we talked about to change the strength of the magnetic field. I'll go ahead and tell you them. Number of turns in the coil, the amount of current flowing through the wire in the coil, and the magnetic permeability of the core material. All right, so those are ways that you can change the strength of the electromagnet. We also talked about the right-hand rule for current carrying conductors. That's an important concept. So if I showed you a wire or a conductor, and I told you current was flowing through it in a certain direction, you should be able to apply this and tell me the direction of the magnetic field around that conductor. All right, and that applies for electromagnets too. If I gave you an applied voltage and I showed you a wire that was wrapped around the core of an electromagnet, you should be able to tell me which side is the North Pole and which side is the South Pole of that electromagnet. All right, and then we talked about generators and induced voltage. And we talked about how to change the induced voltage. How to change the induced voltage. And this is what I was just mentioning. These are different than these. How to change the induced voltage value is different than how to change the strength of an electromagnet. Those are 2 different concepts. And we talked about the minimum requirements for generator action. Minimum requirements for generator action. What are the minimum things you have to get an induced voltage? And that induced voltage, we talked about that in the context of Faraday's law, which is the basis for all generators. And so you should know how to use Faraday's law and solve equations for Faraday's law like we did a bunch of times in example problems over the past month or so, as well as the labs that you've been doing. And to find what the polarity of the induced voltage is, you can use the right-hand rule for generators. All right, so make sure you're comfortable using the right-hand rule, where the thumb gives you the direction of motion of the armature, the conductor, and the first finger is the direction of the field from north to south, and the second through fourth fingers give you the direction of the current that would flow as a result of the induced voltage. All right, but just remember, what you get is an induced voltage, and that causes current to flow. All right, you don't directly get an induced current, you get an induced voltage. And then if you have a complete circuit, you'll get current to flow. Okay, so Faraday's law was one of the big equations that we used in this section. The other was the generator RPM equation, N equals 120F divided by P, where P was the number of magnetic field poles in the generator. So make sure you're comfortable using this equation. We did some labs on that to manipulate the number of poles in the generator and the design of the generator, and to speed up or slow down the generator speed and what effects would those have. So that all comes from this generator equation. And we talked about the construction of AC generators and DC generators. Construction of AC and DC generators. Remember, we talked about AC generators first, and then we said, well, there's just a couple of different things. There's two different things that you have to do to turn your AC generator into a DC generator. One had to do with split ring commutators, and one had to do with adding more coils on the armature. Okay, that was most of the section on generators, and then we flipped to a different topic, and that was motors. And in a sense, motors are just generators operating in reverse, right? Because with generators, your input is the rotation, and your output is electrical energy. And the motors are the opposite. You put in electrical energy, you apply a voltage, and your output is the motion. So they're actually really designed, in most cases, quite similarly. All right, so motors, you need to know the minimum requirements for motor action. Right, you gotta have a current carrying conductor, and it's gotta be inside of a magnetic field. And if that's the case, then you'll get a Lorentz force. And if you have your Lorentz force applied to something that can rotate, then you will get a torque and you will get rotation at the output. We had to apply the left-hand rule for motors in order to determine which direction the motor would rotate, or which direction is the applied voltage, and things like that. And remember, your left-hand rule is very similar to your right-hand rule for generators. Your thumb gives you the direction of the Lorentz force, which is going to cause motion if it's free to rotate. And then your first finger is the direction of the field from north to south, and your second through fourth fingers are the direction of the current flowing through the armature as caused by the applied voltage. So make sure you can contort your left hand around and make that fit. And if I give you any two of those, you should be able to solve for the third thing. All right, then specifically for DC motors, we spent a couple days talking specifically about DC motors. You should know the different types and the pros and cons. I'll just write plus and minus. Pros and cons of each different type of DC motor and how they're constructed. I'll just say and construction, or how they're wired. You know, how you'd build a series DC motor, or a shunt DC motor, or a compound, or a permanent magnet DC motor. And we talked about transients. All right, so I'll figure out a way to ask you some question about transients on the exam. I'm not going to ask you an essay question, so it's not going to be like, tell me step by step what happens if I increase the applied voltage to a DC permanent magnet motor. I won't ask you something like that, but I'll figure out some way to ask some question related to DC motor transients. So with transients, there's really only 4 different things you can have. You can increase the voltage, you can decrease the voltage, these are the applied voltages, or you can have your load go up or your load go down. All right, and that was, these questions, in fact, were the lab on DC motor transients. So you've already got all 4 of those in your notes if you did the lab. All right, so that's most of the topics for DC motors. And we talked about AC motors. And we talked about their different types of AC motors and their pros and cons and their construction. How do you build a synchronous AC motor? How do you build an induction AC motor? What are the different kinds of rotors for an induction motor? You should be able to describe those. We talked about the concept of a rotating magnetic field, which is the single biggest difference in operation between an AC motor and a DC motor. So related to the rotating magnetic field, how fast is it rotating? How fast is it rotating? Well, we can answer that by solving for the synchronous speed, right? And that equation, I'm going to go ahead and write that out because it's a little bit different, if you remember, from the generator RPM equation. So there's the equation for synchronous speed. It's really similar to the equation for generator RPM that we just talked about, but there are a few differences. First of all, it's the synchronous speed now, so it's S. And the second big difference is this P right here. So this is not just the number of poles that you see on the stator. This is the number of poles per phase. So that's really important. If you don't recognize that, then you'll calculate it incorrectly. We talked about the concept for an induction motor. So let's clarify that. For induction motors, and there are two kinds, right? One is a squirrel cage induction motor, and the other is called a wound rotor, which just means it has a bunch of coils of wires on it. For either of these induction motors, which are really important, these are the most common type of AC motors, so they're really important and really common. We talked about the concept of slip. That was the relative difference between the rotation of the synchronous speed, which is the rotation of the magnetic field around the stator, and the rotor speed, how fast the rotor is rotating. And that's that slip, that relative motion, is what creates the induced voltage in the induction rotor, which then causes current to flow, which then causes a Lorentz force and gives you motor torque, et cetera, et cetera. We talked about transients for induction motors only. Transients, kind of like transients for the DC motor. For the DC motor, the different transients were the voltage increases, the voltage decreases, and these are the applied voltages, or the load increases or the load decreases. The way we control the speed of an AC induction motor is not by the voltage, not primarily at least. It's actually by the frequency. So you could have the applied frequency increases or the applied frequency decreases, or still the load increases or the load decreases. So we had our, to answer these types of questions, we had our AC motor wheel o' fun. Just like for the DC motor, we had our DC motor wheel o' fun. And for our single phase, so we had both multi-phase, mainly three-phase, but I'll say multi-phase AC motors, and we also had single-phase AC motors. And one important concept under the single-phase AC motor was, how do we get that rotating magnetic field? Rotating magnetic field. How do we get it? And the answer was, in many cases, in most cases for single-phase AC motors, the important component that we have in there is a capacitor. All right, so we have a capacitor wired in series with one of the windings on the stator of the single-phase AC motor. And since we have a capacitor in there, and since, this is what I'm getting at, since we know that in a capacitor, current leads voltage, Therefore, the current is out of phase in the winding that is connected to the capacitor as compared to the winding that is not wired to the capacitor. And so because the current is out of phase, that's going to do kind of the same thing as we showed back when we were talking about a two-phase AC motor, a two-phase motor. Remember, I showed you a video about that, the rotating magnetic field with two phases. And then I said, well, actually, in real life, usually they're three-phase. But the two-phase actually applies very nicely to the single-phase AC motor where you have one set of windings with the capacitor. So that acts very much like a two-phase AC motor would. All right, that's most of the things on AC motors that I can think of. Transformers. And you should know something called the turns ratio. That's a very common parameter about transformers. So if you talk to somebody who say designs or builds transformers, turns ratio is a common industry term used to describe transformers. We've also got, for lack of a better word, we've got the voltage ratio, and we've got the current ratio. And just remember, when I set these equal to each other, remember the turns ratio is N sub P divided by N sub S, primary divided by secondary windings. Voltage ratio is primary voltage divided by secondary voltage. Current ratio is secondary current divided by primary current. So make sure you are familiar with these equations, because you'll definitely have to use these equations. I might give you the turns ratio and the primary voltage, and you have to find the secondary voltage. Or I might give you the turns ratio and the secondary current, and you have to find the primary current, things like that. So you need to be very comfortable using, there's really just kind of two equations where you set these things equal to each other for transformers. All right, I don't guarantee that is absolutely comprehensive of everything that we've talked about in this second third of the class, but I think it's pretty close. That's everything that came to mind as I was writing that stuff down. So I think it's pretty close to comprehensive. If you have any questions about anything, please feel free to stop by my office hours tomorrow at the usual time. I won't see you next Monday. We will not meet in a synchronous format because we have the exam next Monday. So good luck on the exam. On Wednesday, next Wednesday after the exam, we'll start the last third of the class. And the last third of the class deals with AC electrical circuits. And the topic that we'll start with in that is capacitors, which is kind of nice. I think I've mentioned this before, but I like the way this kind of is laid out because we've already talked about capacitors. You already know the basic fundamentals of how capacitors work. So introducing capacitors in the last third of the semester, it's not such a big shock because you already have an introduction to them. So you already know a little bit about capacitors, but we'll talk more about them and how to use them in circuits in the video on next Wednesday after exam 2. And then I will see you again synchronous on a Zoom session the Monday after that. So that would be April 12th. On April 12th, we will meet in a synchronous Zoom session, and we'll talk about inductors, which are the other major component that's a little bit different that we use in AC circuits, but not so much in DC circuits. So that's about it for today. Let me know if you have any questions. Good luck on the exam on Monday, and I'll see you next time.